Hi students, now we'll talk about section 3.1 chapter 3 position and velocity vectors. Okay, look here, if we have x, y, z direction, we need them ordered as the right hand right hand rule. From x, if I move my finger from x to y, then the thumbnail, this finger will direct to z direction. If we have two positions, position 1 and position 2, the house and the school, okay, the house are located by vector r1, the school is located by vector r2. Okay, the first position vector from the origin to to point 1, which is the house r1, is equal to x1 I hat plus y1 j hat plus z1 k hat, and the second position vector is r2, which is x2 I hat, y2 j hat, and z2 k hat. If we move from point 1 to point 2 and we have been at point number 1 at time t1 and we go to the point number 2, the position number 2, and we arrive there at t2, then we have delta t between the two situations. So we have delta t going through this time. Maybe we have a third position, fourth position, and so on, r3, r4, and so on. We just need to change the name of the components of each vector. It will be x3, y3, z3, and so on. Is that understood? This vector is vector or position vector. Also, this is another position vector. Okay, when we move from the first point to the second point during a period of time, we have speed because we have changed our position during a time. The change in position, the rate. What is the rate in change in position with respect to time? We can take delta r as vector, which is r2 minus r1. How can we do that? By using the components. We have delta x, which is x2 minus x1, because we have r2 minus r1. We need just to do this operation, x2 minus x1, y2 minus y1, z2 minus z1. This is the change in position using the components. Okay, what is the speed in x direction? As we know, the average speed is equal to delta x over delta t. Delta x is known, which is x2 minus x1 over t2 minus t1, which is delta x over delta t. What is the instantaneous velocity or speed? It is the limit when this rate of change, its time limit is 0. It will be dx over dt. And the same for vy and vz. We have the velocity in y direction and the velocity in z direction is dy over dt, dz over dt. Okay? Now, the components x, y, and z tell us about the position vector r, and the components vx, vy, and vz tell us about the velocity vector v for each position or for each moving body. This is the position vector, and this is the motion in this direction. This is v vector. It is not the same as r vector. So we have now r is equal to x I hat, y j hat, z k hat, as we know, and v is equal to vx I hat plus vy j hat plus vz k hat, where we can write v in this view also, which is dr by dt, which is the rate of change in the position with respect to time, which is equal to dx over dt I hat plus dy by dt j hat dz by dt k hat. This is vx, vy, vz. And the magnitude of each vector, as we know using the Pythagorean theorem, the length of the position vector, which is the x component squared plus y component squared plus z component squared under the square root, and the speed, which has no direction, the magnitude or the norm of this speed is equal to vx squared plus vy squared plus vz squared under the square root. Now we need to look to this example. For a moving object with the position vector r as a function of t, we have the three components in x, the x component, y component, and z component. Each component depends on the time. So x is equal to, x component in this vector is equal to 3t squared in I hat plus 2t squared plus 4t to the 4 j hat plus 100 k hat. It is independent of t. So x of t, y of t, z of t. What is the vector, the velocity vector? Simply, it is the derivative of the position vector. V of t is equal to dr over dt. This is x of t. We need to derive it with respect to t. 3t squared, it will be, its derivative is 6t. It is 2 multiplied by 3. And the power 2 will reduced by 1. It will be 6t I hat plus the derivative of this term is 4t plus 16t cubed in j hat, and the derivative of 100 is 0 k hat. We don't have z component for this velocity. For example, now we can find the position and the velocity at any time. For example, at t equal to 0, we need to find the initial velocity and the initial position. What is r at t equal to 0? We just need to put 0 in the place of t. So it will be equal to 3. If we put 0 here, it will be 0. If we put 0 in y component, it will be all 0. And there is no t in the z component. So the position at t equal to 0 is 100, because the x component and the y component are zeros, but we have 100 in k hat, which is altitude, for example, in 100 meters. Also, you need to be careful that by the dimension analysis, 3t squared, we have r, it is a position, it is a length. Then all the term 3t squared is length. So 3 here has a units. Also all the term, this term is a length. Also 100 is a length. So if we need to know the dimensions of 2 or 4 or 100 or 3, we can do it. Also for the velocity, each term has a dimension length over time, which is the unit, because it is velocity. So this unit here is meter per second, meters per second, meter per second. Now the position, it is 100 meter in k hat. What about the velocity at t equal to 0? Okay, we have the velocity vector, it is 6t and 4t plus 16t cubed in j here. If we put 0 in t, it will be 0 everywhere. Then the initial velocity will be equal to 0 meters per second. And we can do that for any t. We can choose any t and put it in the relations and find the position and the velocity vectors for this example or any other example. Thank you. Hi students. Now we'll talk about section 3.2, which is acceleration vector. As we before talk about the position vector and the velocity vector, now we'll talk about acceleration vector. Starting with the position vector, which is r as a function of t is equal to x of t in I direction, y of t in j direction, z of t in k direction, and we find the velocity vector by deriving take the first derivative with respect to time, and we find vx, vy, vz in I, j, k directions, which is the first derivative of the position vector. The same way we can find, as we know from before, that the acceleration is the first derivative of the velocity and the acceleration is the second derivative of the position. So the first derivative with each component for the velocity, and the second derivative for each component for the position vector will give us the acceleration, and the acceleration will be equal to ax, ay, ez in I, j, k direction. Okay, now it is a simple idea. Let us look at this example. If we have position vector as a function of time, cosine, sine will be used, maybe just a simple function, linear function. So r is equal to 10 cosine pi t in I direction plus 5 sine pi over 2t in j direction plus 10t in z direction. We need to find the acceleration vector and the velocity vector, and then find the position and the velocity and the acceleration at t equal 30. It is easy. Just we need to put 30 in the place of t for these vectors. Okay, the velocity vector is the first derivative of the position vector, and we need to derive each component with respect to time just once. Okay, so the velocity vector will be negative 10 pi sine pi t in I direction plus 5 over 2 cosine pi over 2 t j direction plus 10 k direction. The derivative of cosine is negative sine. The argument inside the cosine is pi t. We need to derive it. It will be pi, the derivative of pi t. This is pi, and we have 10, and this is 10 pi negative sine. This is the first derivative of the x component of the position vector in I direction. What about the y direction? The 5 is 5. The derivative of sine pi over 2t is pi over 2 cosine pi over 2t, and 10t, it will be 10 if we derive it. What about the acceleration? It's the same. We need to derive the velocity vector. The derivative of cosine is cosine. We have the argument pi t. We have that derivative of pi t is pi. Then we have pi, another pi from inside, it will be pi squared, and we have 10 and the minus from before. In I direction this. What about the y direction? The derivative of cosine is negative sine. We have negative, new negative sign. 5 pi over 2. We have pi over 2 from inside. For this derivative, it will be here pi squared over 2 squared, which is 4. This is the first derivative of the velocity, of the y component of the velocity in j direction. And the derivative of the constant value, which is 10, is 0. So this is the acceleration vector function in time. Now, what is the value of each of them at t equal 30? we need just to put 30 in place of t for the position, the velocity, and the acceleration vectors. Put t equal 30, 30, 30 each time. This will be equal to, it will be easy. Then we have now, and be careful that the angles in radians, if we need to solve it like in this way, the position at r equal 30, which is equal to 10 I hat, 300 k hat, 0 j hat, and the velocity is 0 in x direction, negative 5 pi over 2 in j direction, and 10 in k direction, in z direction. And the acceleration just in the x direction, and we have 0 and 0 in y and z direction. So we have the direction of the acceleration just in one direction, in negative x direction, okay? Because we have here x. In radians, we have sine 30 pi is equal to 0. Cosine 30 pi is equal to 1. This is in radian. Cosine 15 pi is in negative 1. Okay? In radians. Look and note that R, V, and A here are not necessarily in the same direction. We have the position vector in I direction and Z direction, in X and Z, but the acceleration just in X component, has an X component acceleration. Okay, the velocity, it is not in I and J, it is in J and in I and K, in X and Z direction. It is in Y and Z direction, the velocity. So each one of them has its properties and its direction and its magnitude and length. We can find and look at V, find it from the position, and find the acceleration from velocity using the drawing of vectors. You will use that in the lab section. Be careful for that. If we have two position vectors, R1 and R2, we need to find the velocity. It's easy. We need to find delta R over delta T. Delta R, which is R2 minus R1 over delta T. Okay, what is R2 minus R1? We have just our rows. Okay, as we learned before, R2, this is R2, the same R2, minus R1. We need just to add to R2 negative R1. This is R2, this is negative R1. So this is the vector R2 minus R1, which is this one. Because we have this is R1 and this is R2. The difference between them is R2 minus R1. What is the velocity? It is delta R over delta T. This is delta R. This is the same vector. This is delta R. This one is delta R over delta E. Be careful that the units of delta R is in meters and delta T in seconds. Suppose that delta T is 2 seconds. What is the velocity as a vector? The velocity is the delta R vector over 2. It is the same vector in the same direction but with a half length. We need to divide over 2. If the time is 3, then we need to divide over 3, and so on. Is that clear? This is the position vector and this is the velocity vector, and the unit of the velocity, or the velocity because it is a vector here, is meter over second. What about the acceleration? If we have two vectors, v1 and v2, two velocities, for one body had two velocities, it is accelerated as we see here. What is delta v? Delta v is v2 minus v1. This is v2, this is negative v1. We need to add them together. We have, this is the resultant vector, which is delta v, v2 minus v1, and its units is meters per second, as we know from before. Okay, what is the acceleration? What is the acceleration? The acceleration is delta v over delta t, meter per second over second. for units. This is delta V. This is delta V over delta T. Assume that delta T is a third of second, 1/3 seconds. Then we have delta V over delta T. If we divide this over a third, then it will be multiplied by 3. Then the acceleration is 3 times length of the initial change in velocity. It is in the same direction but with different length. Okay, let us apply it in a curvy path. If you see, we have a circle in the yellowish line, and we have a body moving on this surface or this circle. This body has two velocities, v1 and v2, and the magnitude of each velocity is equal to the other. So there is no change in its speed. What is the acceleration? By drawing. Okay, the acceleration is delta v over delta t. What is the direction of it? Okay, this is v2, this is v1. This is minus v1 because they are equal. Look at this point, it gives them an equal length. So this is v2, this is minus v1. What is the resultant delta v between them? This is delta v. If we divide over delta t, it will give us the acceleration direction. It will accelerate toward the center of rotation. Now, for constant speed and there is a change in direction, we have acceleration not equal to 0. What if the speed is raised? Okay, we have, this is v1 and this is v2. It is bigger than v1. That body is accelerated. So what is delta v? This is delta v here. Sorry. This is delta v. This is delta v, but if we divide over the time, it will be the acceleration. In this case also, this is delta v. We will see that. Now, what is the change in velocity? It is v2 minus v1. We need to add minus or negative v1 to v2. This is the resultant vector between them, which is delta v. It is not direct to the center of rotation. It goes in the direction of the bigger velocity, which is v2. Now there is change in speed and the direction, and v2 is bigger than v1. Then the acceleration or the resultant change in velocity will go in direction of the bigger velocity, which is v2. What if v2 is less than v1? Look at this one, v1, this is v2. What is the change in velocity? Is it v2 minus v1? We need just to add negative v1 to v2. Then this is the change in velocity. It is not directed to the center of rotation. Its direction goes to the direction of the bigger velocity, which is v1 or negative v1, in the negative v1 direction. In this case, we need to understand or to see a new definition for acceleration or components for the acceleration. Look at this part of motion, this part. We know that the center of rotation in this direction, and the body moves on the surface, rotates on the surface of that circle. Okay, now in the direction of motion we need to draw or to assume a coordinate system which is XY coordinate system. This coordinate system is rotates and move on the surface of the motion. The parallel direction is tangential to that curve. The perpendicular direction direct to the center of rotation. Now, for the first case, when V1 is equal to V2, we have just a perpendicular acceleration toward the center of rotation, and the parallel acceleration is 0 in the direction of motion. But in the second case, the acceleration has an angle from the radius of rotation. Then we have a tangential component in the direction of motion, and we have a centrifugal acceleration toward the center of rotation. We have two components for this acceleration. And the same way, if we have any change in speed, then we have a tangential component. This tangential component will be in positive direction of motion and in parallel motion, okay, in positive parallel direction to the motion. If the second velocity is bigger than the first one, when the acceleration is positive, and the tangential component will be in the negative direction if we have deceleration, which is the negative acceleration. Be careful for these three cases, and this part of this section is important in the lab section. Thank you. Hi students, now we'll talk about section 3.3, which is about projectile motion. If you look at the scheme in the book, page number 75, the projectile motion, this is the shape of the projectile motion. If we have a body object, and this body have initial speed, and this speed with angle, initial angle. The initial speed is V naught as a vector, and the initial angle is alpha naught. In this case, this initial velocity has two components: the parallel or x component, which is V naught x, and the y or vertical component. When the body moves along this trajectory, this is the shape of that trajectory. At each point, the velocity for that body will change depending on the time and its place. We have two velocities now. We have a vertical velocity and horizontal velocity. In this experiment, in this problem, we neglect the air resistance. There is no any resistance. In this case, first of all, the horizontal velocity component will stay the same. You can see here Vx naught is equal to, this is the first point, second point, third point, and finally we can take as we like points along this trajectory. At point number 1 we have V1x. At point number 2 we have V2, velocity 2, and this velocity number 2 has an x component, which is V2x. Here also we have the third point. This is the velocity. We have x component and y component. This is Vx. Along all the path, the x component is constant. But what if we look at the y component of the velocity? Initially, it is in this direction and this magnitude. But when the velocity comes to the any other point, the vertical component of the velocity will change. For example, at the highest point, point number 2, the vertical velocity is 0. It is a returning point. If we look from this side to the motion, we will see just a body going up and then going down. At the upper point, the vertical velocity is 0, as we know from before. Also, the motion now under the gravity and the acceleration of gravity, which is g, which is minus in direction downward 9.8 meter per square second. If we look to that third point, for example, we have the same horizontal velocity, and we have downward vertical velocity, which is v3. We can compute it, and the velocity vector in this direction, it is its slope with angle alpha. The angle alpha, firstly it was alpha naught, but later it will change. In this case, for example, at point number 2, the highest point, alpha is 0. Here alpha is alpha of t, depend also on t. We can find it, we will see that. Okay, the equations of motions, we have two groups, two sets for equations of motion. If you remember the equations, v2 is equal to v1 plus at, v2 squared is equal to v1 or v initial square plus 2ax, and x is equal to x naught plus v naught vt plus half a t squared. We have two sets of equations. The first set for horizontal motion, and the second for vertical motion. These two sets will reduce because we don't have acceleration in x direction. So any term with acceleration in x direction will go to 0. For example, if we have v2 is equal to v1 plus at, a in x direction is equal to 0. This term will go. And we have, this is vx and this is vx. So vx finally is equal to vx initially. Also this equation, v2 squared in x direction is equal to v1 in x direction squared plus 2ax. The acceleration is 0. Then we have v2 squared is equal to v1 squared, which is the same first equation. So the first two equations are the same. Also x is equal to x naught plus v naught in x multiplied by t plus half a t squared. In x direction the acceleration is 0. So we have just these two terms. This is, if we suppose that x naught is equal to 0 at origin, then we have x is equal to vx multiplied by t. So we have just two equations in horizontal motion, which is x is equal to vx multiplied by t. It is the simple equation of velocity, and vx always equal to vx at t equal to 0, and we start the motion from 0, 0. What about the y? The vertical motion. We have three equations as we said from before. v2 in y direction is equal to v1 in y direction plus a it is that plus a multiplied by t, v2 squared is equal to v1 squared in y direction plus 2a multiplied by y. Also we have y is equal to y naught plus v naught in y direction multiplied by t plus half at squared. Now be careful that we have the acceleration is g and its direction in negative, and g is equal to 9.8 meter per squared second. So the minus sign is for the downward direction. V naught y v1, which is the initial velocity here, or at any initial point. Also here we have g with negative sign. Also we have g also here. So we have, if we have y naught is equal to 0, then we have two terms. So we can find that y is equal to v naught multiplied by t minus half g t squared, and vy is equal to v naught minus g multiplied by t, and y here is equal to 0 if it is y naught. So the first two equations will be the same also. We'll combine it with the third equation. Now we have two sets of equations in x direction and in y direction. Now what is Vx naught? We have V naught as a vector. The x component of that vector is V naught cosine alpha naught. Okay? So if we take Vx we can use it in x and Vx formulas here. We need to put V naught cosine theta in place of x, Vx, because it is constant, which is equal always to Vx. What about Vy? Vy is equal to V naught sine alpha naught. We can use it in the place of V naught in the formulas. So the y formula will be V naught multiplied by t by sine alpha naught minus half gt. Also Vy is equal to V naught minus gt. V naught is equal to in y directions V naught sine alpha. As we know, we have for any motion we have a position vector and velocity vector. Also we can find an acceleration vector. We just need to derive, but the acceleration in x direction is 0 and the acceleration in y direction is negative g in downward. So if we need to write the acceleration vector, it will be equal to 0 in I direction minus g j direction. This is the acceleration vector. It is simple. Now the position vector, we need to take the position components in x direction, which is v naught t cosine alpha, in y direction v naught t sine alpha minus half gt squared in y direction, and the velocity vector is v naught cosine alpha plus v naught sine alpha minus g multiplied by t. If you look to them, they are the first derivative of the position vector. What is the distance from the first point and the initial point, or any, which is r? We can use the Pythagorean theorem to find the distance, which is rx squared plus ry squared under the square root, and we can find the speed of that body, which is vx squared plus vy squared under the root, to find the speed. And we can find also the direction of that speed, by using the tan inverse relation, which is tan inverse to Vy over Vx. Okay? Now, if we need to find, you know that from mathematics, this is x squared, for example, and this is relates to x cubed, which is a function y is equal to x cubed, and this is function y is equal to x squared. This is a trajectory function, okay? If we need to know the shape of our trajectory, that means we need to write y as a function of x to know the shape of our trajectory. We have the equations y and x, and we have a third parameter, which is t. We need to remove t from both of these equations and use it to connect them. From the first equation, we can find that t is equal to x over v naught cosine alpha. Then we need to put this value of t in y equation. Then we will find that y will be equal to sine over cosine, which is tan alpha naught multiplied by x, minus g over 2 v naught squared cosine squared alpha x squared. It is just like the equation y is equal to a plus bx minus c x squared. It is a parabola formula with negative sign. With that means the parabola direction is not upward, because the minus sign, it is downward. And a, which is the constant, is equal to 0. It is the starting point. Depending on c and b, b is equal to tan alpha naught. c depend on g and v naught and cosine alpha. Depending on the values of b and c, we have different altitude and range for the trajectory, but all of them are parabolas. Is that clear? Now let us solve this example for an object projected horizontally from an edge of a table. If we just hit it, and this object will have horizontal velocity v naught, the angle, the initial angle is 0 from the x axis. If the magnitude of that velocity initially was 2 meters per second, and the body will move with, it will have its velocity and an angle from the x component alpha of t, it will change, but initially it is 0. Alpha 0 is equal to 0. In this case, we have two components, Vx and Vy. We need to find the position vector and the velocity vector as a function of time. Then we can apply any time. We can put 2 seconds, 3 seconds, as we like. And we need to find that with respect to the edge. Okay? Now, we need just to use these equations. And we need to find the position vector and the velocity vector. Now, for horizontal motion, Vx naught is equal to V naught cosine alpha naught, but alpha naught is equal to 0 and cosine is 0 is 1. V naught is equal to t as given. So Vx is always equal to 2. What about the position? The position is equal to V naught t cosine alpha, as we find from the first sheet. Okay, V naught is equal to 2. the time is equal to time. Cosine alpha naught is 0, and cosine is 1. Then we have the relation x is equal to 2t. This is the x component for the velocity and the position. What about the y or vertical motion? We have Vy naught is equal to V naught sine alpha naught. Alpha is 0, sine will be equal to 0. Then the velocity initially it will be equal to 0. It is just like a free fall object. But if we look to this falling object from the side, we will see it as a free fall. Okay? We can use the velocity relation, which is V naught sine alpha, which is equal to 0, sine alpha naught, minus g multiplied by t. G, it is 9.8. So the velocity will equal to minus g multiplied by t. What about the position? The position is equal to V naught multiplied by t, sine, which is equal to 0, sine alpha naught, minus half gt squared. Then y will be equal to minus half gt squared. Now we can write the position vector and the velocity vector. We just need to r is equal to rx in I direction minus half gt squared, which is ry in j direction. This is this is rx, the x component of the position, and this is the y component of the position. And the velocity, this is the x component of the velocity, which is constant, and this is the y component of the velocity. So we have the r component, the position vector and the velocity vector. These two vectors for our example are the same. These two position and velocity vectors are obeying these two relations, the position and velocity vectors. Always we can use them and find these vectors directly. What about the direction of the velocity? Tan alpha at any time is equal to Vy over Vx, I'm sorry, which is minus gt over 2. So alpha at any time will be equal to tan inverse or arc tan 2 minus gt over 2. You can put any time you need in these relations and find the position, the velocity, and the direction of that velocity at any time. Use t equal 1, 2, 3, 0 as you like. That's all for the first part of trajectory projectile motion. Thank you. Hi students, now we'll talk about some examples about projectile motion. Some examples and like projectile motion from a cliff, or full projectile motion as we see here from an origin point, and we have the whole curve as a parabola. Maybe also we have like this, we can change the angle of the projectile. Then we have different shapes of the projectile motion. Also sometimes we have this shape of examples. We have a gun with a projectile motion for the bullet, and another falling body. We have two trajectories, the free falling body trajectory and the projectile motion trajectory. We need to make an equal between these two trajectories and find which angle, for example, or which velocity, or at what time we can hit the target. All of these examples are use the same principles, which are the position and velocity vectors. Let us now look at this example, starting with this. If we look at this gun or cannon, we have a projectile. The X motion is constant. We can see that different places, the different horizontal places for the projectile are the same distance, have the same distance. This means there is no change on horizontal velocity or speed, which is in X direction. Look at the trajectory of the vertical speed. We have different or increasing in the places of each time. This means we have acceleration, because each time we have more distant or past distance. Okay, this is just a note. Now we have this example. By the way, we have 6 pages to solve this example, but I solve it in details. Because of that, I spent 6 pages. We have during Independence Day calibrations. A cannonball is fired from cannon on a cliff toward water. The cliff height is 100 feet. The velocity V0 is 600 feet per second, and the angle is 30 degrees above the horizontal. It is 30 degrees. So we have the givens is the velocity, initial velocity, we have the angle, we have the height. We need to compute some things. We need to find the maximum height of the cannonball. The maximum height is at this point, as we see. We can compute it from our origin, which is the cliff edge. We can find this height, or we can find all the height. We just need to add h to it. Also, we need how long it will take to reach the final point. We need to compute the total time, the flying time. Also, we need to compute x, which is the range. This is sea level. So we need to start solving our problem by some systematic steps. If we look at page number 77, we will see in the purple square there is a strategy to solve projectile motion. At the first, we need to define our coordinates. I will take the origin at the edge. I will take this as an origin. Okay, so this is x positive, this is y positive, this is y negative, this is x negative. I have this positive x, and downward is negative y. So next, I need to clarify the known quantities. The known quantities is phi naught, which is 600 feet per second, alpha naught, which is the angle, h, which is the height, which is 100 feet. What is the unknown quantities? The flying time, all the flying time, the maximum height, the range from this origin to the final point. Okay, we need to understand the sentences and the words here, and I think the sketch can explain that to us better. We need also to find the samples. What is the formulas? We will see that. We will use, as we said before, the position vector and the velocity vector. Then we need to execute and put the known parameters in their places in our formulas. So we need now to start with position vector and velocity vector as we found them before. We have just two coordinates, x and y. X to the right, y to the above direction. We will not use z direction. We have motion in 2 dimensions. So the position vector is has x component and y component. Also the velocity vector has x component and y component. And these components come from equations of motion. We know them. Then we need to evaluate. We need to find the results or the unknowns. In our example, we need to be careful that we have V0 600 feet. We need it in meters. And alpha is 30 degree. It's okay. And H, which is the height of our origin above the sea level, is 100. So the height of the sea level is minus 100 feet. And the reference is the edge of that cliff. This is the second sheet. Now we need to find our velocity in meters per second. Our velocity is 600. This is in details. Feet per second. But I need to multiply it by the conversion coefficient, which is 1 over 3.28. Every 1 meter is equal to 3.28 feet. I need the feet in the denominator to cancel it with the original unit. So the velocity will be 600. The seconds are the seconds. We have still the meter, and 600 is multiplied by 1 over 3.28 will be equal to 182.88 meters per second. We can approximate it, but in general I didn't approximate it. Yes. And the height, which is 100 meters, or the depth of the height of sea, which is negative 100, but I said there h is positive. It's okay. In feet, I need to convert it in meters. It will be 30.48 meters. Maybe you can approximate it to 30.5. Okay, A. We need to find the maximum height. At the maximum height, at this point, the velocity at this point, the vertical velocity will be equal to 0 because it is a retaining point. The velocity, vertical velocity means Vy is equal to 0. Okay, from where can I bring Vy? From the velocity vector. This is Vy. This is Vx. This is Vy. I should put it equal to 0. This is Vy. V0 sine alpha minus Gt is equal to 0. V0 is known. Alpha is known. G is known. I have unknown T. Then I can find T at the highest point. I need just to order the equation, the formula. Then T will be equal to V0 over G sine alpha. This is at maximum height. Okay, what else? I can find T. Just put V0 G sine 30. It will be 9.3 seconds. Okay, this is my trajectory. My projectile takes time T to go up. This is going up or rising time. It is 9.3 seconds. Now we know the time to be at Y max. We can apply this in the position vector. What is the position vector? As we see, this is the position vector. I can put the time in X component or in y component. If I put t going up in the y component, then I will find y going up or y maximum. I will use y component in the position vector. From the position vector, this is the position vector again. This is ry, or the height, this relation. So if we compute the height, we need to use the time going up at the maximum height. So just I need to put t in t. If I use that, v naught is known, alpha is known, this is t, g is known. Just I need to find the numbers, then the maximum height above the reference. This is the velocity vector from the reference. It is 426.3 meters from the cliff, but from the sea level I just need to add h. This is h, so it's 456.78 meters above the sea level. Is that clear? This is the first requirement, A. B, what is the time that's required to go all the path, or the flying time, all the time? I can compute it at the final point using the vector position again. I know where's the vector position. This is the vector position. I know the coordinate of phi at the final point. It is -100 feet. Y is equal to -100 feet below my reference point. So I know ry, or y position, vertical position. So I can use the y component from the position vector, which is equal to v naught t sine alpha naught minus half gt squared, which is equal to -h, -30.48. This will allow me to find the time. I have in the second power relation square the time. I need just to reorder this relation and put theta equal 30, v naught equal to 182 and something. Then I have my final relation is equal to t square minus 18.65 t minus 6.22 is equal to 0. I will use the general formula to find t. T is equal to -b plus minus b square minus 4ac over 2a. b, this is a, which is 1. This is b, which is negative 18.65. c is equal to -6.22. I just put them in this relation, and we have plus negative. We have two values, so we have two mathematical values, but just one accepted physics value. We have two values for the time at that point, which is equal to 19 seconds or -0.33 third a second. This is we cannot accept this value. We can accept this. So the total time is 19 seconds. What about this value? This value, if we draw the rest of our trajectory, the time mathematically from here to here is negative 0.33, or the time from here to here. We can, but there is no motion in this place, so we can't take this value of time. This is the second requirement. We have the final one, which is short one. We need to find the range. The range is simple. The range is from the reference point to the end point. This is the reference, x equal to 0, to the final point. We have the time. We have the velocity. In x direction, it's constant. So from position vector, we have the x component, which is Rx, equal to V naught multiplied by T by cosine alpha naught. We have V naught, we have T, the flying time, we have alpha naught, which is equal to 30. The range will be is equal to 1 kilometer, 737 meter, 0.36, all in meter unit. So this is the range. I solve this example in details and make it long, but repeat it many times, it will be more simple. Thank you.